In this video, we will look at statics of particles. Okay. So, scalars versus vectors. So, what is a scalar and what is a vector? Scalars are quantities like mass, time, volume, speed, right? All of these are scalars and they are completely defined by a single value, right? Mass of a body is 70 kgs, or time is so much, 5 seconds or 10 seconds. It's a single scalar value, right? Single value. Now vectors are quantities that have both magnitude and direction, and in some cases, in most cases, point of application or point of origin. So let's say you have a vector, like quantities like position, velocity, acceleration, force, moment, torque. All of these are vectors. Okay, so a vector, okay, let's say is something like that. It has a point of origin or a point of application. So there are, so let's say this is our x-axis and this is our y-axis. Okay, so now you have a vector. Let's call this P for position of this point. Let's say the point has coordinates x and y. Now how do we write the vector? Vector P with an arrow on the top equals to x I cap, okay, we'll look at, and y j cap. So again, what is I and j cap? We'll get to that. So what this means is, if you want to go from the origin to the point P, you need to travel x units along this axis and y units along that axis, and y units along that axis. Okay. So now we'll define what is I cap. So what is I cap? I cap is a unit vector So by definition, the magnitude of I cap is 1. So magnitude is 1 and the direction here is along x-axis, right? So this is I cap. So I cap, we can, let's say this is I cap, and j cap is a unit vector. Okay, that didn't come out straight. J cap is along, okay, this is j cap. J cap is a unit vector along y-axis. All right. So let's say P has a length of 6 units. So now then, so since this is a right angle triangle, you have the length of OP, right? So we'll call it P is 6 units. This should be equal to x square plus y square. So now P is the magnitude of the vector, and let's say, and is this now completely defined? No, you also need to specify the direction of the vector, meaning the theta, right? The angle which it is making with the x-axis. Now let's say theta is 60 degrees. Now the vector P now can also be written as, what is x in the right angle triangle? You have, this is 6 units, this is 60 degrees, and this is 60 degrees, and this is 6 units. So your x coordinate is 6 cos 60 degrees along I cap along the axis x-axis plus 6 sine 60 degrees along j cap. So this is your x and this is your y, right? Okay. So now the vector p can also be written as in a different way. So now just like we have defined I cap, which is a unit vector along, just like we have defined I cap, which is a unit vector along the x-axis, and we have defined j cap, which is a unit vector along y-axis. So we can also define another unit vector. So this is I cap and this is j cap. We can also define another unit vector. Let us call it p cap, right? Because it is along p. This unit vector is along, this is 60 degrees, right? So let us say p cap is a unit vector along p. So how do we determine p? The vector p divided by the magnitude of the vector p. So this is simply cos 60 degree I cap plus sine 60 degree j cap. So this will be another unit vector just like I cap and j cap. You have p cap, which is unit vector along p. Okay. So now your vector p can be written as p times p cap, right? Okay. Right. Now let us look at, so if the vector is in the first quadrant, we have, let's say this is x-axis, this is y-axis, right? So if the vector is like that and it is, let's say 5 units and this is 4 and this is 3, right? So here your vector is p vector is 4 I cap plus 3 j cap, right? Because you travel, if you want to go from O to P, you have to go 4 units along I direction, and this is I, right? I cap, and this is j cap, right? Now if your vector is in the second quadrant, right? Let's say it is something like six units here and 4 units here, then this will be something 4.5, right? Right angle triangle. So then here your vector p is 4 units minus I cap plus 4.5 units j cap. So vectors, you need to be very careful about the direction. So your I is still this and your j is this. I, this can come out straight. Let me erase it. Yeah. Your I is this and your j is that. Okay. So now just similarly, if your vector is in the third quadrant, let's say this is 5 units and 4 and 3. So in this case, this is your O, this is your P. So here your P vector is minus 3 I cap, or 3 times minus I cap minus 4 j cap. So I and j are in the positive x and positive y directions. That is how we have defined them. So finally, if your vector is in the 4th quadrant, let's take this 6 and 4, and this is 4.5, then your P vector is 4.5 I cap minus 4 j cap, right? So depending on which quadrant your vector is in, you have to very clearly mention the direction of the vector. Okay. So if you have noticed, we have put the I and j. This is your x-axis, this is your origin, this is your y-axis. So unit vectors are free vectors, meaning, so now there is a difference between free vector and a non-free vector. So if you take a position vector, you have to, in order to completely define the vector, you need to mention the magnitude, the direction, as well as the point of origin or the point of application, or a starting or the end point of the position vector, or else the position vector is not completely defined. If you say P is a position vector which is 6 units and is at an angle of 6 units in magnitude and 60 degrees with positive x-axis, making 60 degrees with positive x-axis is not enough. You need to also either show in the diagram or mention its start point or end point. Only then you will know where the P vector is from, or else P can be anywhere. I can have P here. This is also 6 units and this is also making 60 degrees, but it's not the same as this. So in order to define a position vector, you need to define it completely or specify it completely. In case of a unit vector, on the other hand, you can mention, you can say this is I cap. I cap is a unit vector in the direction of x-axis. Even if you put it here, it doesn't matter. It is still a unit vector, meaning its magnitude is unity 1 and its direction is in the x direction. I can say this is j cap, vertically upwards, and its magnitude is unity. It is completely defined. You can place it anywhere. Okay. Right. So we need to define the orientation of the vector very clearly, right? 60 degrees here, 60 degrees with positive x-axis. Even this is not completely defined, because if you say 60 degrees with positive x-axis, I can also show another vector which is also making 60 degrees with positive x-axis. So you need to mention 60 degrees with positive x-axis counterclockwise, meaning from here, if you are measuring it counterclockwise, then it is 60 degrees. Right? Now it is completely defined. You need to mention the direction in which you are measuring. 60 degrees with positive x-axis measured counterclockwise. So from, with respect to, right? So with respect to positive x-axis, meaning you are measuring starting from the positive x-axis and going towards the vector P. So then it is counterclockwise. So that is how you completely define a vector. Okay. Now you can extend this vector definition to 3D. Just include, so P is Px I cap plus py j cap plus pz k cap, and then you have magnitude of p, which we will write as simply p without the arrow on top is equal to square root of px square plus py square plus pz square. Okay, and then you also can define p cap, which is unit vector along the direction of p, which is vector p divided by the magnitude of the vector p. So this is px by p I cap plus py by p j cap plus pz by p k cap. Now that is what is the unit vector along p. So now how will we determine the direction, right? So if you take a vector, right, p, right, from the origin, right. So this is your x-axis, this is your y-axis, and this is your z-axis, right? X, y, and z. So for a 2D or planar vector, it is simply p makes an angle of 60 degrees with positive x-axis measured with respect to positive x-axis measured counterclockwise. That is how we define it. Here it's a 3D vector, so you can use the what are called direction cosines. Right, which is simply the angle between, this is theta x, the vector, and the axis x, and theta y. So measured always from the axis, right? This is theta y and measured always from the axis theta z. So how do you get this? Simply cos inverse px by p is theta x. Similarly, cos inverse py by p gives theta y, and cos inverse pz by p gives theta z. So these are the three angles. So this is how you completely define the orientation of the vector in 3D. Let us look at resultant of a force, right? Forces are vectors. Resultant of a force. Okay. So let's say there is a particle in space and there are two forces acting on the particle. Force P and force Q. Angle made by this is 60 degrees, let's say theta, and angle made by the force Q is, let's say, 70 degrees. Now what is the resultant of these forces? Resultant resultant is simply the summation of the forces, right? So we can have a particle in space which is acted upon by n number of different forces, let's say 10 different forces. So it would be easier to look at as simplify the system. So you always add the forces. So you need to simply add the forces. Now let us look at each of the force vector. So your resultant is Q plus P is the resultant, let's say it's called R. Let's look at each force. P vector is P cos 60 degree along y-axis plus p sine 60 degree along j-axis, and my q vector is q cos 70 degree, and that is along minus I cap plus q sine 70 degree pointing vertically upwards, which is j cap. So your resultant, let's say P is 10 newtons and Q, magnitude of Q is 12 newtons, right? Okay. So now your resultant R is, add these two, you have P, or P is 10, right? Okay. 10 cos 60 degree minus 12 cos 70 degree plus 10 sine 60 degree plus 12 sine 20 degree, right? Okay, sorry, this is I cap along axis and this is along j axis. Now this will be equal to, I don't know, minus 6.3 I cap and plus 12.8 j cap. So your resultant will be that you have to travel minus 6.3 and 12 point minus 6.3, let's say here, and 12.8. This is 12, right? So 6.3 will be around half of it here, and then 12 will be right maybe there, right? Okay, somewhere there. Okay. So this is your resultant R. This will be the resultant of these two forces. You can also determine the resultant graphically, right? You have P and Q. Let me take some other color. So you take the P and add it to Q here. So this is supposed to be parallel to P. Okay. Okay, you can also get the resultant graphically. We'll do it separately. Let's say P is this and Q, P is this and Q is this. Okay, Q is this. Now you can draw a what is called a polygon, vector polygon. So you take this is P and this is Q, vector P. This is vector P and this is vector Q. So you now draw a line parallel to Q from the end point of P. Let's assume that's parallel, and then you say parallel to P. So that will be your resultant, right? So this is a parallelogram. So you construct a parallelogram with P and Q as the sides, and the diagonal will give you the resultant, right? Or you can construct a triangle, right? Put Q here, and whatever is the third side of the triangle, you will have that is the resultant. Okay. So you have P at 60 degrees, then 70. So this is 60, this is 70 degrees. Okay. So now this is your P and this is your Q. So this will be your result. So that will be the resultant. Okay. So this is graphical. Solution. Okay. So you can also do it graphically if you have only two forces. If you have multiple forces, you keep on adding, you will get a polygon, right? So we have our resultant R is minus 6.3 I cap and 12.8 j cap. So how do we define, how do we specify this completely? Also have to mention the angle made by the vector. So it is minus 6. So whatever that angle is, we compute that angle and say resultant R makes theta degrees with positive y-axis measured counterclockwise. So you are measuring from positive y-axis counterclockwise this way, right? So that is how you give your answer. You can't simply leave it at minus 6.3 I cap and 12.8 j cap. You also have to get the angle for the resultant vector. Forces, right? Let's say you have 1, 2, 3, 4, 5 forces, right, acting at same point. You can simply do a parallelogram to get the resultant of these two. Once you have the resultant of these two, you can remove this and this, right? Now you get resultant of this R of these two, and then you get that is your resultant. Then you remove this and this, and then you do a resultant of these two. Which is that. So you can then remove these two and then do a resultant of the last remaining two. So from here you draw a line parallel, make a parallelogram with these two as the sides, right? no, that, and then that. So this will be your final resultant. This is your final resultant. So R will be summation of F1 plus F2 plus F3 plus so on. So you can do a series of parallelograms and then determine the resultant, or you can write x and y components, get x-axis, y-axis, and then write the x and y components and add all of those to find your resultant. Any which way, resultant is simply summation of all the forces. Is summation of all the forces. Now, resolution of a force. So you have a force vector. So we are looking at how do you resolve a force vector. What is called resolution. Okay. So you have a vector. Let's say it is acting like that. This is vector A. Now, vector A can be written as vector B plus vector C, right? Let's assume this is a straight line. This is vector B. So vector A can be written as vector B plus vector C. Now the same vector A can also be written as vector B plus vector C, right? A, B and C vector. Again, same vector can be written as vector B plus vector C. So you can, basically resolution of a force is again opposite to summation. You are dividing the force, right? You can do it in any which way. Any way is fine. Now, these are called, B and C are called components of vector A. These are called components. Components of vector A. These are the ones that we see here are not orthogonal, meaning not perpendicular to each other. And hence they are not independent. So what does that mean? That means you can, if you extend this line here, vector C can also be again resolved along B and perpendicular to B. C also has components. Even here you can, right? C can again be resolved into two components. One is along B and along C. So now if you take the vector A and do it along x-axis and along y-axis, which are perpendicular to each other, then let's say this is A and this is B now, and this is C. Now, B cannot be resolved along C and C cannot be resolved along B. They are mutually perpendicular, right? So B and C. These are orthogonal and are independent. It is always ideal to resolve a force vector into orthogonal components. Okay. So here, which is what we do when we are doing along x-axis and y-axis. Okay. So let's say we have a force vector F. which has, this is x-axis, this is my y-axis, and this is my origin. This is my force vector. This is fx and this is fy, right? Force vector is fx I cap plus fy j cap, right? So now this is my, this is called f, let's call it fx is fx I cap. This is the projection, is the projection of force vector f onto x axis, right? So, and fx is the component, or you can say is the component of f along x axis, right? Projection and component means pretty much the same thing, right? Okay, so now your f can be written as fx plus fy, right, which is fx I cap plus fy j cap. I can also choose my two different unit vectors or axes. I'll call this u axis and I'll call this v axis. This is, and now I will write my force vector as u cap, which is unit vector along the u axis, plus v cap, which is a unit vector along v axis, right? So this is also possible. So let's say u is at an angle of, this x-axis is at an angle, u-axis is at an angle of theta with x-axis. So your u, unit vector u cap is like that. So this is making 60 theta or 60 degrees with x-axis, or j cap, sorry, I cap. So now my u cap is cos 60 degree I cap unity, right? Magnitude is 1 plus sine 60 degree j cap, and my v cap unit vector, which is perpendicular to u cap, is cos 90 plus 60 degree I cap plus sine 90 plus 60 degree j cap, right? So magnitude always of unit vector is 1, is also 1. Okay, so you can write it this way or you can write it this way. So vector can be defined in any which way, right? So fx will be component of the vector along x-axis, fu will be component of the vector f along u-axis, right? Okay. So we'll need to find components, then we can do that. Now let us look at dot product. Dot product. Okay. So traditionally we have learned dot product as a vector A dot vector B equals to magnitude of vector A times magnitude of vector B times cos of theta, where theta is the angle between vector A and vector B. This is theta, vector A, vector B, then this is your dot product. Okay. So now we have 3D vectors. And we are writing our vectors as ax I cap plus ay j cap plus az k cap, right? And then we are writing our vector B also as bx I cap plus by j cap plus bz k cap. Okay. So now if you do a dot b, right, let us do it like that, ax. So now I dot I is both I vector dot I vector, so the angle is 0, so cos of the angle 1, so ax bx, ax times, if you multiply this times this, right, ax by I dot j, so I and j cos 90 0, so that thing vanishes. So if you write it, you will simply get ay by plus az bz. This is your dot product. So another interesting thing is, if you have vector A and you do a dot product with I cap, so this is, what is this? Magnitude of A, magnitude of I cap is 1, and cos of angle made by A with x-axis, which is cos theta x. Or if you write it differently, you can also write it as ax I cap plus ay j cap plus az k cap dot I cap. This is simply ax, right? So this is component of A along x-axis or along I cap, right? So if you want a component of a vector along some u cap, right, that you define, you simply do, you find A, and let's say u, like we defined earlier, u cap is cos theta I cap plus sin theta j cap, right? Now if you do a dot product between these two, then you will get, this will be ax cos theta plus ay sin theta, right? This will be the component of A along u cap or along u axis. Okay. So if you want a component of a vector along some axis, you find a unit vector along that axis and you simply do a dot product of the vector with that unit vector. Okay. So you have A P cap equals to so this is how we can write component of A along P, right? Okay. So sometimes the projection is written as A dot P cap, since it is along P. So here's how it is written. So you can also write it as vector A dot product with vector P times magnitude of P squared times P. So this is a scalar quantity. So you are simply scaling the vector P with this quantity. So this is projection of A onto P, right? We have done this before also when we're doing the dot product. So if you take your just for the sake of completeness, this is I cap, J cap and K cap. So we have I cap dot I cap is K cap dot K cap equals to 1, right? We also have dot J cap equals to J cap dot I cap equals to 0, right? We're missing something here. K cap dot J cap equals to K cap dot also equals to 0. Everything is 0 because these are all vectors that are perpendicular to each other. Okay. And A dot B is same as B dot A, right? So the dot product is commutative and A dot B plus C is A dot B plus A dot C. So it is distributive. Dot product is also distributive. Okay. What else? Okay. Equilibrium of a particle. So we are looking at statics of particles. So in that we look at what is equilibrium. What comes to mind when we say equilibrium? When we say equilibrium, what we mean is balance, right? Or everything is static, right? Not moving, equilibrium. So when a particle is said to be in equilibrium, what that means is sum of all the forces acting on the particle is equals to 0. So your resultant is 0. And since we are writing the forces as components of fx, fy, fz, we can also say that sigma fx equals to 0. Sum of all the force components along x-axis equals to 0. Sigma fy equals to 0 and sigma fz equals to 0. Right. So when we have three forces acting on a body, right? Let's say there is a particle acted upon by three forces, 1, 2 and 3. So there are three forces acting on the body, and let's say this is A, B and C. So if you draw the polygon, right, so there is no resultant. Your resultant is 0. That means if you make a polygon with these three forces, in this case it's a triangle, it has to be closed, so it will form a triangle, right? If you make a polygon with these, it will be a triangle. Okay, 1, A, B and C, right? This is vector A, this is vector B and this is vector C. Let's say this is angle A, this is angle . So these are angles A, B and C. So now if you apply sine rule, right, sine of A by magnitude of vector A equals to sine of angle B by magnitude of vector B equals to sine of angle C by magnitude of vector C. So now sine of A is same as sine of 180 degree minus A, right? A is sine of 180 degree minus B, then this is same as sine of 180 degree minus C. Why are we doing this? We'll look at. Okay, so this angle, right? What is 180 minus B? This is 180 minus B, right? This is 180 degree minus B. What is 180 degree minus C? If you extend this line, this is 180 minus C. And if you extend this line, this is 180 minus A. So this is angle between B and C. If you look here, between B and C, this is same as this, right? So this is 180 minus A. This will be 180 minus B. This is 180 minus C. See the angle between A and B, right? Vector A is like this and this is vector B. The angle between them is 180 minus C. So this is basically Lami's theorem, right? Lami's theorem. What this says is, when three forces acting at a point are in equilibrium, then the magnitude of each force is proportional to the sine of the angle between the other two. So that is what this is, right? Okay. So to to write it vectorially. Vector A plus vector B plus vector C equals to 0. Right? All the x components, y components, z components should add up to 0. Now, so as long as we are looking at triangles, if you have, we'll quickly write A, B, C, A, B and C. This is B, this is C and this is A. We also have cosine rule. A square equals to B square plus C square minus 2BC cos A. B square equals to C square plus A square minus 2AC cos B. C square equals to A square plus B square minus 2AB cos C. Right. And if you have a right angle triangle, then theta, just for the sake of completeness, you have A is C cos theta and B is C sin theta. Okay. Now, let's say we have a vector in 3D space. We have a vector in 3D space, a force vector F, and we have coordinates of 2 points A and B, and we know that the vector F and vector F is acting along line joining points A and B, right? So this is AX, AY, AZ, this is BX, BY, BZ. This is my origin O. So the position vector A or OA is AX I cap plus AY J cap plus AZ K cap. Similarly, we have OB is BX I cap plus BY J cap plus BZ K cap. So now when we know that vector F, the force vector F, is acting along line joining AB, what do we know? We know that they both have the vector from A to B, right? Vector AB is vector AB and the force vector have the same direction, right? They are both different. AB is a position vector, F is a force vector, but they both have the same direction. So AB is from A to B. So OB minus OA, right? So OA is this. So you have OA and you have OB, OA and OB. So we want AB, right? So you go from O to point A, OA, and then from A to AB. So OA plus AB should be OB, right? If you go from O to B, or if you go from O to A and from A to B, it should still be the same, right? A and B. So OA plus AB will give OB. So AB is OB minus OA, right? So how do we write our vectors? We can also write our vectors as AB is equal to magnitude AB, magnitude of the vector, which is, we write AB without the arrow on the top, times AB cap, which is unit vector along AB, right? And this unit vector is same as the unit vector along the force, right? F is force F magnitude times the direction. So now AB cap is equals to F cap, right? Both the unit vectors are same. Now AB and AB are in meters, right? Because they are distances and vectors, distance, position vector. F and F are in newtons, force and force vector. The unit vectors are dimensionless. So once you know the unit vector AB, you can use that in as F cap and to determine the direction of the force. Okay. I think we'll stop it here.